Next, the world's most advanced telescope took another leap forward this afternoon as its mirrors were unfolded 1 million miles from Earth. NASA's James Webb Observatory is the successor to the Hubble Space Telescope.
The third ever interstellar object observed from Earth, currently racing through our solar system now. Astronomers have captured that moment live.
When the James Webb Space Telescope trained its unmatched gaze toward the mysterious interstellar visitor known as 3I Atlas, it did not just capture an image, it confirmed a truth that astronomers had long suspected, but never proven. This wandering object, the third known interstellar body to pass through our solar system after Oumuamua and Borisov, has been the subject of heated debate since its discovery. For months, speculation swirled about its origin, its composition, and even whether it represented a new class of celestial object altogether. Yet, Webb's latest observations have decisively shown that 3I Atlas is precisely what many theorists believed all along: a frozen relic from another star system, behaving in ways that illuminate both the universality and diversity of planetary formation across the galaxy. Before we start, hit the like and subscribe buttons for more updates. The first hints of 3I Atlas's identity came from its erratic trajectory. Like Oumuamua before it, the object followed a distinctly hyperbolic orbit, meaning it was not gravitationally bound to our sun. It swept in from deep interstellar space, curved briefly through the inner solar system, and then arced back out, destined never to return. Unlike Oumuamua, however, 3I Atlas displayed unmistakable cometary activity, a coma of sublimated gas and dust trailing behind it, whispering of volatile ices awakening under sunlight. But ground-based telescopes, constrained by distance and the faintness of the object, could not tell whether that coma came from familiar substances like water and carbon monoxide or from something more exotic. That was where the James Webb Telescope entered the picture. Webb's infrared instruments, optimized for peering through dust and detecting faint molecular signatures, were the ideal tools for the job. As 3I Atlas approached perihelion, the point closest to the sun, Webb focused its mirror and spectrographs on the faint drifting glow of its tail. The resulting spectra were revelatory. Peaks in infrared absorption clearly corresponded to the vibrational modes of water, carbon dioxide, methanol, and traces of ammonia, compounds common in comets formed in the cold outer reaches of planetary systems. In that moment, the debate ended. 3I Atlas was not a metallic fragment, not an alien probe, not a purely rocky asteroid. It was a bona fide comet from another star system, carrying the chemical fingerprints of a birthplace light years away. The significance of that finding cannot be overstated. For decades, astronomers have built models of how comets form within protoplanetary disks, those vast, swirling clouds of gas and dust that give rise to stars and planets. They assumed that such processes were not unique to our solar system, but evidence was limited to our own backyard. 3I Atlas provided the first direct sample, through its light, its composition, and its behavior, of material forged around another star. The Webb data revealed striking similarities to solar system comets, confirming that the recipe for building icy bodies appears to be universal. It also revealed subtle differences, particularly in isotopic ratios and the balance of carbon-bearing molecules, which hinted at the unique chemical environment of its parent system. In essence, Webb had detected not just another visitor, but a messenger carrying a record of the conditions in a distant cosmic nursery. What made the detection even more astonishing was the level of preservation. Interstellar travel is a brutal journey. Cosmic rays, high-velocity dust collisions, and eons of isolation tend to erode the delicate structures of icy bodies. Yet 3I Atlas still retained enough volatile material to form a visible coma under solar heating. That suggested it had been ejected from its home system relatively recently, perhaps within the last 100 million years, a mere blink on galactic timescales. The likely scenario is that gravitational interactions with a giant planet or a passing star flung it outward, turning it into a wanderer between the stars. This mechanism mirrors how our own Oort cloud could send comets outward under similar disturbances, meaning that every planetary system might contribute to the interstellar background of rogue comets. The Webb telescope's data offered another crucial insight: the object's surface temperature and outgassing rates. By comparing the strength of spectral lines with models of sublimation, Astronomers could estimate how much material was escaping from the nucleus each second. They found that 3I Atlas was venting gas and dust at rates consistent with mid-sized solar system comets, not the hyperactive outbursts seen in smaller or freshly fragmented bodies. This indicated that it had a stable nucleus beneath the surface, perhaps tens of kilometers across, coated in layers of dust that insulated its deeper ices. The implication was profound. It meant that interstellar comets can survive long journeys intact, preserving the primordial chemistry of their origin worlds for billions of years. When scientists analyzed the ratios of deuterium to hydrogen, DH, in its water vapor, a key diagnostic of where in a planetary system a body formed, they discovered values similar to those of solar system comets originating beyond the frost line. This finding suggested that 3I Atlas had formed in the outer regions of its home star's disk, beyond the point where temperatures were low enough for water and other volatiles to condense. Such regions are fertile grounds for planet formation, meaning this interstellar traveler likely hailed from a system with gas giants capable of gravitationally ejecting comets. Webb's precision measurements therefore linked the chemistry of a foreign star's outer disk to the dynamical processes we understand from our own solar history. One of the most surprising revelations came from the detection of organic molecules in 3Y Atlas's coma. The mid-infrared spectrum displayed complex carbon-bearing features, consistent with simple organics such as formaldehyde and perhaps even ethane or acetylene. These molecules, though common in solar comets, take on added meaning when found in interstellar material. They demonstrate that the chemistry necessary for prebiotic compounds is not confined to our solar system. It may be widespread across the galaxy. In that sense, 3I Atlas became not only a window into another planetary system, but a hint at the universality of the ingredients for life. Webb's imagery also offered a visual spectacle. Even from millions of kilometers away, its sensitive instruments could resolve the faint fan of the comet's dust tail and the symmetrical halo of gas around its nucleus. Computer models derived from these images suggested that the particle size distribution was similar to those seen in solar system comets, dominated by micron-scale grains. The orientation of the tail and the rate of its curvature under solar radiation pressure allowed astronomers to estimate the object's rotation period and axial tilt. The data indicated a slow rotation, perhaps once every 10 hours, and a stable orientation, suggesting that it had not undergone recent fragmentation. All of this contributed to the growing picture of 3I Atlas as a fully natural, well-behaved comet, behaving precisely as models predicted, except that it came from another star. As more spectra rolled in, Webb's instruments detected subtle variations in emission over time, implying localized jets or vents on the nucleus surface. These active regions released bursts of vaporized ice and dust as they rotated into sunlight, a dynamic behavior seen in many solar comets. The similarities were almost poetic. This alien visitor, born under an alien sun, followed the same rhythms as the icy wanderers we have known for centuries. It was as though the physics of sunlight and ice conspired across the galaxy to produce the same ephemeral beauty wherever conditions allowed. The confirmation of 3I Atlas's true nature reverberated through the astronomical community because it validated decades of theoretical work about interstellar comet populations. Models had long predicted that each planetary system, during its formation and evolution, would eject trillions of small, icy bodies into interstellar space. Most would drift invisibly, their faint reflected light lost in the glare of distant stars. Only occasionally would one cross paths with another system, offering a fleeting glimpse into its alien chemistry. Oumuamua had raised that possibility but confused the picture with its lack of a coma and odd acceleration. Borisov seemed more comet-like, but was observed under less favorable conditions. 3I Atlas, observed by the most advanced space telescope ever built, provided the definitive proof. By confirming that interstellar comets share key properties with solar system ones, Webb also constrained the physical processes governing planetary system evolution. The fact that these bodies form under similar conditions elsewhere suggests that disk chemistry, temperature gradients, and volatile condensation zones are not unique features of our solar nebula. They are the natural outcome of physics operating consistently across the cosmos. This finding strengthens the idea that planets like ours, and perhaps habitable environments, may also be common. If comets everywhere share similar compositions, then the raw materials for life, the water and organics they carry, must be distributed on a galactic scale. The data from 3I Atlas also offered practical lessons for future exploration. Astronomers used Webb's precision to refine techniques for rapid response observations of transient interstellar objects. Because such visitors move quickly and fade fast, capturing them demands coordination between telescopes and adaptive scheduling. The success of the 3I Atlas campaign demonstrated that the infrastructure developed for time-sensitive astronomy, initial detection by survey telescopes, rapid trajectory calculation, and immediate handoff to space observatories can now operate with near-flawless precision. This capability will be crucial when the next interstellar body is discovered, potentially within just a few years. Beyond the immediate technical triumph, the detection rekindled philosophical reflection on what it means to study something so ancient and alien. Every comet in our solar system tells a story about the early days of the Sun, but 3I Atlas carries a story from somewhere else entirely. From a star whose light may not even reach us yet. It is a fragment of a world that may have long vanished, yet through the laws of motion and chance it crossed our path. To measure its light is to touch across light years the residue of another dawn. The spectroscopic fingerprint of 3I Atlas also helped astronomers refine their understanding of interstellar dust chemistry. By comparing its features with those of interstellar medium absorption lines, scientists concluded that the comet's material had been processed within a disk environment rather than remaining pristine interstellar matter. This distinction is key. It means that the object was part of a mature planetary system, not a remnant cloud. Its ice ratios bore signatures of thermal processing, ultraviolet irradiation, and mixing, hallmarks of disk evolution. Essentially, Webb allowed scientists to diagnose the developmental stage of another star's planetary formation history from a single passing visitor. Further analysis of the thermal data showed that 3I Atlas's nucleus likely contained stratified layers formed during its accretion. These layers, each with slightly different chemical compositions, corresponded to varying temperatures and pressures within the disk. When heated by sunlight, gases escaped preferentially from the upper layers, revealing a pattern of activity that mirrored comets from our own Kuiper belt. The comparison confirmed that planetesimal formation processes, aggregation of ice and dust under low temperature conditions, follow similar pathways regardless of which star they orbit. An unexpected twist came when scientists modeled the orbit backward in time to estimate its origin. Tracing its hyperbolic trajectory through galactic coordinates, they identified a region of probable origin within a few hundred light-years, possibly linked to a young stellar association in the direction of Hercules. While the exact source star remains uncertain, this estimate provided a tantalizing clue. 3I Atlas may have come from a region still rich in planet formation activity. If so, it could represent a sample of material from one of the galaxy's most fertile stellar nurseries, a time capsule from the earliest epochs of planetary creation. The James Webb Telescope's role in this discovery underscored its unparalleled sensitivity. Observing an object so faint, moving so rapidly against the background of stars, pushed the limits of the telescope's tracking and calibration systems. Engineers had to account for parallax, variable illumination, and motion blur at speeds exceeding 30 kilometers per second relative to Earth. Yet Webb's adaptive optics and infrared sensors performed flawlessly, capturing clean, detailed spectra that would have been impossible from the ground. The success proved not only the telescope's scientific value but its engineering mastery, expanding the range of targets that future missions can pursue. The broader implications of 3I Atlas's detection ripple through multiple disciplines. In astrobiology, it bolsters the theory of panspermia, the idea that life's building blocks can be spread between star systems via comets and asteroids. If interstellar comets routinely pass through planetary systems, depositing organic compounds as they go, then the chemical seeding of life could be a galactic-scale phenomenon. Each passing object might deliver trace amounts of prebiotic material, slowly enriching young worlds over eons. Webb's detection of organics on 3I Atlas gives that theory tangible support. In planetary science, the findings refine our understanding of how systems evolve dynamically. The ejection of comets like 3I Atlas requires gravitational interactions strong enough to overcome stellar escape velocity, implying the presence of massive planets in the source system. Thus, every interstellar comet we detect indirectly confirms the existence of exoplanets, giant worlds capable of slingshotting debris into space. By cataloging the trajectories and compositions of such comets, astronomers can infer statistical properties of exoplanet populations far beyond what direct imaging can reveal. The detection also influences our concept of cosmic connectivity. For the first time, scientists can empirically study material that has crossed the vast gulf between stars. Each molecule in 3I Atlas's tail was forged in an alien environment, traveled for millions of years through interstellar space, and then sublimated under our sun's light to tell its story through Webb's instruments. It is a reminder that the galaxy is not a collection of isolated systems, but a dynamic ecosystem where matter continuously exchanges between worlds. The dust of one system becomes the seed of another, and the boundaries between solar systems blur in the grand sweep of cosmic evolution. The confirmation that 3I Atlas was indeed an interstellar comet did not mark an ending, it marked a beginning. With its shimmering coma caught in Webb's gaze and its molecular fingerprint decoded, the object opened an entirely new dimension of astrophysical inquiry. What Webb revealed was not merely a distant visitor frozen in time, but a narrative stretching across the galaxy, a living testament to the physics that unites all planetary systems. Yet the details, its dynamical behavior, subtle variations in brightness, and the implications for galactic population models deserve exploration far beyond the initial announcement. To understand what Webb truly uncovered, one must dive deeper into every layer of this extraordinary cosmic encounter. When the telescope tracked 3I Atlas through its outbound leg, researchers noticed delicate modulations in brightness. These fluctuations, though small, were rhythmic, suggesting a rotation that was neither uniform nor perfectly smooth. The pattern hinted at a tumbling motion, a slow precession perhaps caused by uneven outgassing jets on its surface. Cometary bodies, especially those that have journeyed through the void for millions of years, often develop irregular shapes and spin states. The loss of material from asymmetric vents can act like tiny thrusters, gradually altering rotation over centuries. For 3I Atlas, this tumbling motion painted a portrait of long isolation, a body that had been slowly reshaped by micro-impacts and solar encounters across eons before it ever neared our system. Detailed modeling of these light curve fluctuations, combined with infrared thermal data, provided a rough outline of the nucleus, elongated, possibly cigar-shaped like Oumuamua, though larger and more cohesive. The Webb data suggested a body roughly 50 to 80 kilometers in its longest dimension, enveloped in a dark carbon-rich crust that absorbed sunlight efficiently. This darkness, a characteristic seen in solar system comets, results from organic compounds baked and reprocessed on the surface, forming a protective mantle over the ices beneath. Such mantles act as insulators, allowing interior volatiles to survive even during close stellar flybys. In this way, 3I Atlas resembled a survivor of multiple ejections, perhaps passing near several stars before reaching us. The question naturally arose, how many times might it have brushed past other suns before ours? Galactic dynamics are not static. Stars drift, cluster, and separate over millions of years, and gravitational perturbations constantly alter the paths of small objects. By simulating its trajectory backward in time, astrophysicists estimated that 3I Atlas may have wandered for tens of millions of years, weaving through different stellar neighborhoods, each passage potentially altering its surface chemistry slightly through radiation or heating. It might even have passed close enough to another planetary system to briefly glow again before freezing anew in interstellar night. Each such encounter etched a new layer onto its history, a palimpsest of cosmic journeys recorded in molecular ratios. Webb's data also allowed scientists to probe the density and thermal inertia of the nucleus. By measuring how quickly the surface cooled as it rotated into shadow, they deduced a surprisingly low thermal conductivity. The material was fluffy, porous, and filled with voids, a classic cometary structure known as a rubble pile, formed from loosely bound aggregates of ice and dust. This porosity explained its resilience. Rather than shattering under stress, it flexed, dissipating energy through its open internal network. In galactic terms, this made 3I Atlas a tough traveler. It could survive high-velocity dust collisions, cosmic ray exposure, and even near-miss encounters with stellar winds without disintegrating completely. Another layer of insight came from the examination of its coma morphology. Webb's near-infrared images revealed subtle asymmetries, slightly denser material in the sunward direction with faint arcs suggesting periodic jets. These arcs are like fingerprints of localized vents. By modeling their spacing and curvature, astronomers inferred that specific regions on the nucleus periodically erupted as sunlight reached them. These jets likely originated from subsurface pockets of carbon monoxide or carbon dioxide ice, which sublimate at lower temperatures than water. Their detection confirmed that 3I Atlas retained multiple volatile layers from its original formation zone, a crucial clue that it formed beyond its parent system's snowline, where temperatures were frigid enough for complex ices to condense. The implications extended beyond chemistry. The comet's dynamical behavior provided evidence for the gravitational architecture of its original home. To eject an object into interstellar space requires a precise dance of celestial mechanics. A planet, usually a giant, akin to Jupiter, must impart a strong gravitational kick at the right moment. Too weak, and the comet remains bound. Too strong, and it disintegrates. The existence of 3I Atlas implied the presence of at least one massive planet in its parent system, orbiting far from its star, acting as a cosmic slingshot. In this way, each interstellar comet becomes indirect evidence of exoplanetary systems that might otherwise remain invisible to telescopes. The isotopic analysis of 3I Atlas's gases added another dimension to this portrait. The ratios of oxygen-18 to oxygen-16 and of carbon-13 to carbon-12 showed subtle deviations from terrestrial values, hinting that its parent star might have formed in a slightly different part of the galactic disk, where the interstellar medium's composition varied. These isotopic fingerprints allowed astronomers to place constraints on the object's birthplace within the Milky Way. If, for instance, its isotopic balance matched those observed in stars of the Perseus arm, that would suggest a long voyage from one spiral arm to another, a migration spanning thousands of light years. Such a journey illustrates the dynamic churning of our galaxy, where matter is constantly exchanged between regions through stellar winds, ejections, and gravitational encounters. Further insights emerged when scientists examined the dust grains released from its coma. Though Webb could not directly capture individual particles, their collective scattering properties were encoded in the reflected light spectrum. Analysis revealed a predominance of silicate grains mixed with carbonaceous compounds, similar to the composition of comets within our own system. However, the grains were larger on average, suggesting slower accretion or weaker turbulence during the comet's formation. This subtle distinction pointed to variations in the density and viscosity of its parent protoplanetary disk. Such differences, though minute, offer astronomers new parameters to refine models of how planetesimals grow around young stars. The observation of silicate emission bands also confirmed that the dust contained crystalline structures, implying that it had experienced heating above 1000 Kelvin at some stage, likely early in the disk's history near its central star. The fact that such material was incorporated into a body that later formed far from the star demonstrates the effectiveness of radial mixing in protoplanetary disks. Hot material from the inner regions can be transported outward by turbulence and embedded within icy bodies. This process, observed in our own system, now appears to be a universal feature of disk evolution. Through one passing comet, Webb had illuminated the dynamic complexity of planetary birthplaces across the galaxy. In addition to compositional data, the energy distribution in its infrared emission allowed calculation of its albedo and surface roughness. The results showed an extremely dark matte surface with an albedo below 0.04, darker than charcoal. This darkness is typical of heavily irradiated comets, where ultraviolet light and cosmic rays transform surface organics into tar-like tholins. The coloration, inferred from visible reflectance spectra, would likely appear reddish-brown if viewed directly. Such coloration is consistent with objects from the outermost zones of planetary systems, confirming that 3I Atlas was born in an environment rich in complex carbon chemistry. While Webb's contribution was central, it did not act alone. Ground-based observatories provided complementary data in visible wavelengths, while radio telescopes detected faint emissions from specific molecular transitions. Together, these datasets created a multi-wavelength portrait of unprecedented depth. The synergy between Earth and space observations exemplified the new paradigm of coordinated astrophysics, distributed instruments operating as a single virtual observatory spanning millions of kilometers. 3I Atlas became a proving ground for this approach, demonstrating that even transient interstellar phenomena can be studied comprehensively with enough precision and planning. In the theoretical realm, dynamicists used the new information to recalibrate models of interstellar object flux. The fact that 3I Atlas exhibited a stable cometary morphology rather than the flattened shape of Oumuamua suggested a broader diversity among interstellar visitors. Some are volatile-rich and behave like comets. Others may be desiccated remnants of once icy bodies. The ratio between these types can reveal how efficiently planetary systems retain or eject their icy components. The emerging picture suggests that volatile-rich ejections are common, meaning that most planetary systems form substantial outer reservoirs similar to our Kuiper belt or Oort cloud. Thus, 3I Atlas provided empirical evidence that the architecture of our solar system is not exceptional. It is a typical blueprint. The Webb team's analysis also deepened understanding of interstellar radiation processing. By modeling how the comet's surface spectrum differed from pristine ice mixtures, researchers inferred the degree of alteration caused by cosmic rays during its interstellar drift. The data indicated that 3I Atlas's surface had accumulated a radiation dose equivalent to several hundred million years of exposure, yet the interior remained chemically unaltered. This preservation suggested that even after immense spans of time, interstellar comets could deliver relatively pristine material if captured by another system. The possibility that such bodies could impact forming planets raises fascinating questions about cross-system material transfer on galactic scales. The trajectory of 3I Atlas through the solar system offered another trove of information. Precise tracking revealed slight non-gravitational accelerations caused by asymmetric outgassing jets. By measuring these deviations, astronomers could estimate the total thrust produced by sublimating gases and, by extension, the surface area of active regions. Interestingly, the acceleration profile matched predictions almost exactly. Unlike Oumuamua's anomalous behavior, this congruence confirmed that standard cometary physics adequately described the object. No exotic propulsion, no mysterious pressure effects, just sunlight and vapor interacting as expected. The satisfaction among scientists was palpable. Here was a case where observation and theory aligned perfectly, vindicating decades of model development. As 3I Atlas continued outward, its fading coma gradually revealed more about the nucleus itself. Webb's instruments tracked the declining brightness and found that gas production decreased exponentially with solar distance, consistent with sublimation models for water and CO2. This confirmed that no internal heat sources existed. The comet's activity was purely solar-driven. By extrapolating the curve, astronomers could predict how long the object would remain detectable, mere months before fading into invisibility. Yet those months were enough to gather an archive of data that would feed analyses for decades. The study of interstellar comets also carries implications for the early history of our own system. Many theories suggest that Earth's water and organic molecules were delivered by comets. If bodies like 3I Atlas are common, then such deliveries might occur across stellar systems on a galactic scale. It is conceivable that the same processes that seeded Earth with life's ingredients also operate elsewhere, with interstellar comets acting as couriers of chemistry between stars. This vision redefines the galaxy as a dynamic network of chemical exchange, blurring the boundaries between planetary systems. In the broader cosmological context, the detection speaks to the efficiency of material recycling within galaxies. When stars form, they inherit dust from previous generations, enriched by supernova and stellar winds. Planets condense from this material, and some fragments, like 3I Atlas, are eventually ejected. Over millions of years, these fragments may find their way into new systems, perpetuating the cycle. Webb's identification of familiar molecules in 3I Atlas confirms that the chemical continuity from star to star is not theoretical, it is observable. The same water and carbon that once froze around another sun now glistened under ours, proving the interconnectivity of galactic evolution. The discovery also reinvigorated discussion about potential capture events. Could our solar system ever permanently capture such an interstellar visitor? Theoretically, if a comet like 3I Atlas passed close enough to a giant planet like Jupiter while moving relatively slowly, gravitational interactions could trap it. Over billions of years, a few such captures might have occurred, meaning that some comets we label as native could actually be immigrants from other stars. Webb's detection provides a reference point for identifying such hidden interstellar residents by their isotopic signatures or unusual orbits. The object's passage also gave astronomers a chance to test observational techniques for detecting interstellar debris belts. As 3I Atlas approached perihelion, instruments monitored the surrounding space for smaller fragments or dust trails. Though none were definitively identified, the methods developed could be applied to future detections, helping to estimate how much interstellar dust accompanies such visitors. This information, in turn, refines models of galactic dust density and its contribution to background light. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on James Webb confirming 3I Atlas discoveries? We want to hear from you. Thank you for watching and see you next time.